In this series of videos I'm looking at this ZAX ICD178 in-circuit debugger. This is for a Z80 and the real purpose of this series of videos is to look at developing some Windows software to control this, to give better visualization of what's going on within the target system. But before we get to that, I just wanted to expand a little bit on its capabilities, what it actually is. There's a bit of confusion sometimes as to the difference between an in-circuit debugger and an emulator. This is not an emulator, it's not pretending to be a Z80. There is actually a Z80 processor inside this. And what this really does is there's a series of multiplexers and buffers, and it allows you to decide which of the address lines, data lines, control lines of the Z80 are targeted towards the target machine, target board. And this allows you to do various things. Firstly, you can of course control the target board or target device, but you can also monitor it when it's running at full speed. You can monitor what it's doing, you can set breakpoints, and you can very easily create test programs within the target device that you're trying to work on. Now you can use other methods. It really depends on how functional the target device is. So for example, if it's not running at all, you can't easily load code into it, and in fact you might not be able to access the memory in it at all. And that's really where something like this comes in, and that's what we're going to look at in this video, is the memory mapping that's available within a device like this, and why you might need it and why it's so useful. There's many reasons why it's useful, but we'll just touch on a few within this video. Before we come to that, I'm just going to expand a little bit on the test programs that we looked at in the previous video, and I'll expand on why the test program, for example, what we showed, always access the same memory location, and we'll go through the various reasons you might want to do that. But the main thing to bear in mind is that when you're testing a target machine, it's not necessarily going to be running at all, and I'm sure everyone has their own ways of looking into the faults and trying to determine what's going on. And something as simple as our target device here, which is a ZX81, you probably don't need something like this at all. It's very useful if you want to develop your own ROM code for this, for example. You could do that very easily with something like this in-circuit debugger. But on a complex machine, it's very useful if you're trying to repair it or make changes to it, specifically because it doesn't need to be functional for you to be able to run the in-circuit debugger, whereas many other methods, the machine has to be pretty functional before you can start running the test code. So in other words, the memory mapping has to all work, the memory itself has to work, etc, etc. That's not true with the in-circuit debugger. The memory on the target machine may not work at all, but you can still run the board using the memory within the ICD. So we'll go over to the PC, we'll quickly recap some of the test programs. I'll expand a little bit on the thinking behind them, and then we'll come back and start looking at the memory mapping that's available using something like this ICD. Okay, so we're looking at the terminal, and the observant of you will notice that I've modified the ROMs within my ICD. I've made a few changes. The later ICDs announce their version number and what particular processor they're for when you boot them up. This didn't do that, so I've included that function. I've made a few other minor changes as well. There were a few bugs that I found while I was reverse engineering it, so I've dealt with those. And I've made a couple of changes just so that it suits me a bit better in the way I will be using it. But very minor changes. It still really behaves the way it did originally, but for anyone playing at home, although it says version 8D here, I updated it from version C simply so that I knew which particular version of code it was running. So this is really version 8C code with the minor changes that I've made to it, but I did not modify the build date. Okay, so the first thing is the test programs we were running, and we'll reload one of them so we can have a quick recap on what it was doing. So we'll load the test code. So I've got the test code itself loaded. We'll put the trace on all. We'll also single step it, and we'll set a breakpoint. And we can now start to run this. Before we do that, we'll have a quick look at the memory that we're going to be targeting with this test. And the address we're interested in here is this 4030, which is currently a value of 0. So we'll now run this. And it's in single step, so I'll keep repeatedly pressing the spacebar. Okay, we'll exit that, and if we now look at the memory again, so notice now at 4030 the value is 55 hex, and if you recall from the previous video, what we were doing was repeatedly writing a value of AA followed by repeatedly writing a value of 55, but it's always to the same address. And I think somebody put a comment on the previous video asking what incremented the pointer to memory, and the answer was nothing. And that might seem a bit of a pointless test, but the reason that I'd start off with tests like this is generally I'm trying to establish if the memory is functional at all, and quite often it's not. I often find faulty memory chips, faulty decoding of memory spaces. In the ZX81 it's very simple, it's a linear single bank memory arrangement, but in almost all the equipment I repair it's multi-bank, fairly complex memory mapped arrangements. So the first thing I do is normally run a test program that repeatedly tries to do nothing but write or read and write the same memory location, and it's even more useful for DRAM systems. So you can look at the CAS and the RAS values and see if there's a problem with the memory addressing, the decoding, or the memory chips themselves. So this is a very good way of determining if there's a faulty memory chip. For example, if you look at all the bits and on each cycle you're getting the correct bit sequence going into the memory chips, if the wrong values are seen coming out, you know you've probably got a faulty memory chip. So we'll have a quick look at some of the code that I tend to run, and the way I have this arranged is for each processor type. So for every processor I'm going to encounter, I will have a specific folder. In this case we'll select the Z80, and I have a series of test programs that I tend to use. Now normally I modify them depending on the particular machine I'm working on because the memory mapping is different. But if we look at the source for these, the one in particular we were looking at in the previous video is this one, and you can see here that this is just I don't compile these, by the way, using a compiler. I just enter them as you saw me doing it in the previous video, or I will manually compile them. A very simple program, so it only takes a few minutes. But what we're doing with this particular test is just looping round writing the same value. If the readback is wrong, we jump to an error and just go round and round in circles at that point. And we do the same thing again with a different value. You can repeat this, of course, for any values you want, but it's always at the same address. Notice that HL is not being modified in this test. But if we open a different test, so the test I normally start with is this one. It's a very simple test, and this is doing something even more basic. It's just writing a particular value to a single memory location, and then it's reading it back. It's not doing anything with the result, and it's just looping around doing that over and over again indefinitely. And it's a very good way you can then put a scope onto the target system and see exactly what it's doing, whether it's working, and in theory at least backtrack and try and figure out why that particular aspect of the system isn't working. Normally by the time you can get this to run, the rest of the system is working fine, or at least the rest of the memory system is working fine. So a simple test like this can help you resolve a lot of issues. And because this is the only thing that's running on the target system, you're not kind of trying to wade through all sorts of weird wonderful things going on with the address bus and the data bus. All that's happening is the system's trying to run this very small tight loop, so you know exactly what's supposed to be going on. And I have similar code for different aspects of the system, in, out, the video area, ports, etc. And you can have very simple test programs, and normally by the time you've got everything working on the system, you should be able to run the code in its entirety. So that's why I was reading and writing the same location repeatedly. If we now load a different program, so this is the next program in sequence, and if we try and run this, so again we're single stepping through this. Normally once you get the system running, you wouldn't single step, you just let it run, and it would go through and complete the test in its entirety. And what the next test does is something fairly similar, and then the next test after that would write multiple addresses, etc. So you just load the programs in sequence and run them that way. So once we've done that, the next thing to look at is trying to run the full code, the ROM code for the target system. So we'll just go back to the workbench, and I'll quickly explain why the ICD can be so useful in trying to do that. So hopefully you can see that having these very simple test programs and something like an ICD can make testing a target system much more straightforward than trying to wade through the ROM code that normally resides on them. So I had been using a combination of my Fluke 9010A and the logic analyzer, scope, etc. to do this. But as I said, I really want to get more use out of these ICDs. I've got a number of them, and I'm starting off with the Z80. But you may also recall, if you've seen my previous videos, that I created a memory accessory for my Fluke 9010A. And the main reason I did that was because I wanted to be able to save all those test programs in such a way that I could very easily configure my 9010A to run them. You can kind of upload the programs from the 9010A. More of the system needs to work than it does if you're using something like the ICD, so it's not always that convenient, and it's also quite slow and doesn't have a lot of the capabilities that the ICD will have. But what I have is a series of these memory cards that I use with my Fluke, and these contain all those same test programs, but in a format that I can use within the Fluke 9010A. So now onto the memory map, and this is where the ICD can be very useful. So what we have is, in the ICD itself, we've got a bank of RAM. So this is, in this case, it's a 64K bank of DRAM. So that's what I showed in one of the previous videos. And on the target machine, then of course we have a memory space that is also at least 64K. Now in the case of the ZX81, it's not all used. We have 4000 hex bytes for the ROM and another 1K of RAM. And the rest of this isn't used, although it's not fully decoded, so if you try and access something up here, you'll actually access something within the ROM or the RAM. But in most systems you'll have multiple banks, you'll have a much more complex memory map. But the problem is it might not work, or the decoding for it might not work, or there may be some issue that's not working in another part of the system. And what you really want to be able to do is run some test programs, or maybe a section of the ROM code. And the way the ICD works is it contains a Z80, and the electronics within the ICD will let you run the target system as if the Z80 was plugged into the target system. So it's kind of seamless as far as the target system is concerned, and the target system doesn't know it hasn't got a Z80 plugged into it. So if you just set it running, it will just access the ROM code in the same way it would if you had a Z80 plugged into it. But where the ICD really comes in useful is in its memory mapping capability. So on a 1K basis, you can map blocks of code out of the target system into the ICD, or vice versa. So for example, let's say we want to have a copy of the ROM code that we can easily modify, rather than having to desolder the ROM chip from the ZX81 in this case, modify the code and put it back in. What we can do, as you've already seen, is very easily extract it, or there's even a command within the ICD to copy it into the memory map within the ICD. So the ICD works in one of three modes. It will either run in mode 0, which is where it completely ignores this and it runs only using the internal resources of the ICD. So that's more akin to a software emulator, something you'd use on a modern system when you don't have any hardware attached. You can run it in mode 2, which is when it ignores all the internal resources of the ICD, and it just runs everything from the target hardware. And then you have mode 1, which is where it's a combination of the two, and you can define a memory map. So for example, let's say we want to run the ROM code from within the memory of our ICD, then we can map that like this, and the memory, the RAM, will be mapped into the actual RAM of the ZX81. And you can mix and match this however you want, but the point now is you can copy the ROM code either directly from the target machine or using the load commands we've already seen, and we can have our ROM code running from here. You can also define it as read-only, so that if the code for any reason tries to write to this, it will cause a break to occur and it will stop the code. Although this is now deemed to be ROM code, you can of course edit it because it's actually in RAM, so you can make small changes to it. The system's not aware that the ROM code it's trying to run is no longer on the target machine. As far as it's concerned, this block of RAM now sits over here and is actually a ROM. And you can do that, as I say, on a 1K by 1K basis, so you can do the same thing with the RAM or any other block of code. For example, if you're working on a CPM machine, you might want to make a modified version of your BIOS, and so that's normally mapped here. But if you want to, of course, you can map it out to the RAM within the ICD, write your own version, make small modifications, and the system again will not know that it's not accessing its own RAM, and it's all seamless. It will just see it as if though this code is actually sitting over here. So we'll go back to the terminal and see how we go about configuring this, and just showing some of the functionality that it gives you. So looking back at the terminal, we can start looking at the memory map functionality of the ICD, and in this case the command is the S command. Now this might not match documents you may have for other versions of this ICD, and this is one of the reasons I had to reverse engineer the firmware, is because none of the documents I could find matched the way this particular unit was behaving. So some of these commands, or all of them, might not match the documents you have for other versions of this type of ICD. But the memory map command is the S command, so with no parameters, if I hit return, it shows us the current memory mapping. And This system doesn't retain any settings when you reboot it, so you have to re-enter everything each time. It's one of the reasons I want to write the Windows software. We've also got this warning that says not in circuit mode 1, and the reason for that, of course, is the memory mapping only makes sense when we're in circuit mode 1, and that will become clearer hopefully as we go through this explanation. So the system defaults to in circuit mode 0 when we boot it up. You can see that's the mode we're currently in, which means that all the resources we are looking at by default are the ones within the ICD itself, including the RAM. So if we look at the lower part of RAM, notice it's just got random data in there, and if we look at the area from 4000 upwards, again that's just random data as well. However, if we switch over to mode 2, which if you recall is where we're looking at all the resources only on the target system, if we look at the memory from 0 upwards, then you might recognize that's the ROM code within the ZX81, and if we look at the area from 4000 up, which is the RAM area, it's just got random data. So what we'll do is, we can't modify the ROM code, of course, it's a ROM, but we can modify the RAM. So what we'll do is we'll fill the area from 4000 up with hex value of 81 for ZX81. And if we re-examine that, notice we've got 81. As I say, we can't write to the ROM area, but we can recognize that anyway. If we now switch back to mode 0 and look at the same memory location, you can see it's completely different. And what we'll do now is we'll fill this block of RAM and we'll put a value of 27 in there. Forgot the H there. We'll try that again. Re-examine that block, and you can see we've got values of 27. If we look down at the lower section, again it's still got random data in there. Well, what we can do is fill that, and we'll fill that with hex values of 17. So as you can see, we've got values of 17 from 0 upwards for the first 100 hex bytes, and from 4000 up we've got 27. So this is in the RAM within the ICD. But if we switch back to mode 2 and look at the area from 0, you can see that's the ROM code, and the area upwards is still set to a value of 81. So you can see they are completely different blocks of code. What we can now do is memory map these. So if we switch to mode 1 and we look at the memory map, you can see all the memory is currently assigned to, it says P here, and that means it's all ICD RAM, and the program memory is all read-write. You can modify any of that. And also notice the warning has gone that was there. So what we can now do, just to confirm we are indeed looking at the ICD memory, we'll look at the lower section first. You can see that's the value of 17 we put there, and at 4000 upwards that is indeed still 27. But what we can do is change that memory map. If we want to, we can change, for example, the lower section. So again, we use the S command, and in this case we want to change the mapping to target system, so we use U, and we give it the addresses we want to use. Look at the memory map. So notice now that it's showing us U from 0 up to 3FF, and it's showing above that P. So U means it's the target system and P means it's the ICD. The reason it changed the 100 up to 3FF is because 1000 bytes is the minimum block size that you can assign in a map. It just picks the nearest one. So now if we look at the area from 4000 up, it should still be the same because we're still looking at that area is still mapped to the ICD. However, if we now look at the lower section, notice that is the code within the ZX81. So in what is now a single apparent memory space, the lower section is the ROM code in the ZX81 and the upper section is the RAM within the ICD. And we can do that for any section of code, any section of RAM that we want. We can change it to read only, we can change it to read write, we can even change it to output, which is where it's neither one thing or the other. So as you can see, this is a very powerful way of controlling memory access. You can also declare each of these areas as read-only output. So if it's neither RAM nor ROM, it might be in the in-out section, you can declare it as such. And it means that you can effectively put RAM into the ROM area of your ICD, and that allows you to make modifications to the ROM. So for example, you could copy this ROM code into the RAM of the ICD and make small changes to it, write your own code. You can do whatever you like, and this is a very powerful tool when you're trying to develop systems, and in particular if you're trying to repair them. Hopefully it's becoming a bit clearer now as to the potential power these have and how useful they can be in fault finding, repairing vintage equipment. And probably the main thing really with them is, as ever, it's a little bit cumbersome having to drive them through a terminal, especially because they don't retain settings, so each time you boot it up you have to reconfigure it. It's not a particularly time-consuming thing to do. It just would be nice if all that could be done in a much easier way. Now you can of course save the commands as script files and just send them all up to the ICD as a file. So you can do that, and that's a very easy way to have kind of pre-configured file definitions when you're working on a particular piece of equipment. But the sorts of things that really make these much more useful is if you have some kind of visualization. So for example, for the memory map, if there was some Windows software that showed you a visualization of the current map, the data flow between various parts, the current registers, without having to call up and kind of read through lines of text each time they changed. It would be nice if all that was presented in kind of real time. Now it won't be real time, of course. It's a serial interface, so there will be delays, but for the most part it could eliminate the need to have to kind of send out manual commands. You just basically set it running, set your memory map, and have some visual feedback as to what was going on, and that's kind of the ultimate goal. But before I get into that, I thought it would be useful just to go through some of the capabilities, and that way as we get into the Windows software, hopefully it will become clearer as to why certain elements within the system development make sense. Otherwise it would be fairly difficult trying to explain why some of the features that I want to build into the Windows system are required. Any feedback is welcome. If you have used one of these, then again any comments are welcome, but hopefully as we get into the Windows software, the whole thing will start to become clearer as to what I'm really aiming for and why I think these are quite useful devices to have.